For the first example on how to add vectors in a physical setting, let's consider an ant moving along a sheet of paper with the edges of the sheet of paper already aligned with the cardinal directions. So first the ant moves 3 centimeters to the west, and then it turns to the right and moves another 5 centimeters in a direction 25 degrees north of west. The question here will be, how far is the ant from its original point? Here's our coordinate system with the alignment of east, west, and north, south, and we're going to start with the first vector for the displacement of 3 centimeters along the west direction. I'm going to draw a vector here d1 with components minus 3 to account for the shift in the west direction of 3 centimeters and 0 y component. Next, I'm going to draw a second vector d2 with components dx and dy. Now, I don't know those components right away, but what I know is that that vector has to make 25 degrees relative to the west direction. So I'm going to use the west direction for my reference line, and I'm going to move towards north at 25 degrees. I'm going to draw a perpendicular here, and I'm going to mark dy for the y component of the second displacement and dx for the x component of the second displacement. I will use sine and cosine here to figure out what those components are. Let's start with the x component. It is the adjacent side in the orange triangle, so it's going to be involved with the cosine function. I will have cosine by definition of theta is equal to d2x over d2. In other words, the x component of the second displacement d2 will be equal to d2 cosine theta, or numerically it is 4.53 centimeters. Notice here I have written it down with minus to account for the fact that that displacement is actually in the west direction, so the shift happens in the direction that is opposite to my positive x. Next, we can go to the y component, and we're going to see that for that we will use the definition of sine. Sine of theta here will be d2y over d2. So I'll have for the y component of the second displacement vector to be d2 sine theta, or numerically it's going to be 2.11 centimeters. So let's take those values and combine them into the whole d1 expression, and we're ready to combine the two trips. Trip 1 represented by vector d1 on my diagram with components minus 3 and 0. Trip 2 represented by the vector d2 with components minus 4.53 and plus 2.11. What remains here is to add the two vectors using the rules for adding by components. So the x component of the total displacement will be equal to minus 3 minus 4.53, or minus 7.53 centimeters total. What that means is that after the ant has moved along those two trips, eventually the ant will find itself 7.53 centimeters to the west from the origin. Now the y component is going to be 0 plus 2.11, or 2.11 centimeters. So for the ant, that means that after the ant is done with the trip, it will be 2.11 centimeters in the north direction. The problem here asks for the distance, actually, how far the ant is from the original point. So I need to use the Pythagorean theorem here and calculate what the magnitude of the total displacement d is. That will come out to be 7.82 centimeters. And that is the answer to the problem. Notice here that even though we know the answer, it's not quite clear how the vector looks. For that, it's always good to go back to the diagram and draw that vector for the total displacement using the graphical geometrical rules for addition of vectors. Just draw the vector. It's always good to have some visual of what is happening.